Good afternoon. So, first of all, let's start from something important. Okay. Yesterday, 2 groups answered correctly my percentage question, if you remember that. So, whoever did this, he didn't put a name. So it's just it's just numbers. So whatever it is, I have no idea. I don't know. Whatever one claims that, I'll take it. And then the other one is a Sean over there. Okay, Sean Moser. Is that what you guys? Who is a Sean Moser here? Because 2 people is difficult. Okay, this is yours? Okay, perfect. Anyone want to claim this? Okay, perfect. In good faith, right? Okay, so I would like to ask you a favor. If do you remember who was in the group with you guys? Do you remember? Yes. More or less? Okay. Could you keep the same groups today? I want to ask you a few more things. So until tomorrow. Tomorrow we'll get some tokens, but I need to collect points. So remember who were your teammates yesterday? Try to keep the same teammates today, okay? So what's your name? Alfred. Oh, we talked yesterday, right? Yeah, okay, so I remember that. Perfect. Okay, so before we start, just to make sure that yesterday you were listening to me a little bit again, if you want to have the same groups as yesterday, whatever you like, guys. So I have 2 questions for you today before we start, but they are based on what I did yesterday. So if you want to participate with your group, if you can answer some questions here, and then give the answer to me, and then I'll screen the things today. So if you want to talk for a few minutes, I would like you to answer those 2 questions for me, a little bit regarding the lecture that we had yesterday, okay? So I want to see what you remember. And then if you can turn in your answers with your group names, possibly, I will keep track of your performance until tomorrow, okay? So I'll give you a couple of minutes just to take a look at that, and we'll go from there. So maybe more question tomorrow, so pay attention to me today, okay? That's the only thing. Okay, so just to review, yesterday we were talking a little bit about the fuel, the chemistry, and the point was that even if you think a little bit about the molecules, you can already kind of infer some of the behaviors that happen, okay? And so with regard to the question I just posed, let's go back to what we learned about the surrogate. Surrogate is basically, you do need that when you need to simulate a system, a real system, and your fuel, for example, is a real fuel. By real fuel, I mean like a mixture of hundreds of compounds, for example. And so the question was, I have a real fuel, and now I am going to a gasoline. It's always weird because I cannot turn, but at work. So, and so if you look at the gasoline, just to remind you guys, what happened is that you have, remember, you have air, you have a fuel, and then usually it's a premixed charge, so it's almost stoichiometric. There is a potential for knock, right? That was the issue. And so with these things, what we talked about was something. It's not even working today. The choice of the combustion properties. I don't know what's happening here, sorry about that. Okay, so that was the question. So let's go back, a little bit of summary of what happened yesterday and what I would like to do today. So yesterday my goal was to give you an overview, to tell you that the combustion process is complicated. That combustion on the other side is a fascinating topic because it's challenging and is you cannot have more complexity, I think. So you have a system that is a high temperature, is very reactive. You have radicals that are playing a huge role. And so while things are growing, there is a reaction, and there is also agglomeration that is a little bit different together with the nucleation. So very complicated system. Time scales is a problem, and And the idea is that if your goal is eventually to have something that is predictive, so that basically going from the fuel all the way to the formation of nanomaterials, then you need to be careful about the different steps. Okay, so we talked yesterday about the physical models, if you remember. If my goal is to model soot, then there is different steps I need to take. I start from my fuel, my oxygen, and then slowly I need to do something in my gas phase. I go from a simple fuel to form benzene, for example, that is one of the major aromatics that you form. And also you grow in size here with this pH's formation. So polycyclic, aromatic, hydrocarbons, they grow. So this is all the gas phase that happens. Once you reach a certain size, the question is, I translate, somehow I convert in these nanoparticles. People see experimentally some of those, mainly with optical technique. The question is, how does this happen? And we still do not have an answer to that. So once you form those, basically, and again, the transition is the least understood, now you have multiple things going on. You have some kind of solid phase that is formed. They start to coagulate, but you also have a surface growth from the gas phase. So you still have a small molecule that can be added to those clusters that you form. Once you have that, eventually you will have this coagulation, agglomeration, and eventually some oxidation. So the black is soot. What I'm very much interested, and I want to maybe pause for a second on this, is this kind of a transition. How do I go from here to these nanoparticles? What I was mentioning is also that it's tough for experimental people to do that because the region is very narrow and things are very, very fast. So people sometimes sample before, in which you have the concentration of pHs. They sample some of the particles after. But how this happens is still an unknown process. There are ideas. There are people think, two major pathways that I'm going to highlight today, but still they don't have a clear answer. The other issue is that the time scale, because I'm going to come back to this later with molecular dynamics. The problem is that if I want to just grow this material, like this point, and then instead of talking about spheres, like we did yesterday, I want to be more specific and think about molecules, so the chemical composition. Then the time scale is a problem because I'm growing here with 10 milliseconds, but if you have a molecule, the molecule can also rearrange while it's growing. And usually those phenomena are different. You can have a microsecond, picosecond. So how do you put everything together? I think that's the question here. So let's go back now to the beginning. I told you yesterday that basically there are soot models that are available. There are discrepancies. Some of the soot modeling, you can have the method of moments. You can have the sectional models. And going through these steps, you can have coagulation, coalescence. But really what you want to be starting from the beginning is that the gas phase needs to be correct too. Okay? Otherwise, everything that you do after is influenced by what you have. The other thing that I was mentioning is this yesterday. The problem is that for the gas phase only, you have a lot of mechanisms that you find in the literature. So, for example, you have experimental work, you want to try to model. Model is important to predict. For example, you measure some stable species, but you don't measure everything. So the model can give you information about that. And so here, the problem with this graph is that if you look at the literature, different groups are developing modeling, number of species, number of reaction. Over time, we're going in this direction. So eventually, we will have an explosion, basically. You have too many reactions, too many species. And already, when you're interested in an engine or CFD, you need to reduce mechanisms because this is too much. A lot of this information also is not necessary. Okay? So one of the questions that you want to think about is that what are the important pathways that you want to keep in mind for that? What are the things that are driving the process in some conditions? And even if people do that, even if they have these huge mechanisms sometimes, then this is an example of the result I was showing yesterday, in which they measure the concentration of the species, but what you see in terms of the modeling is a huge discrepancy. Again, log scale, so what you see as a discrepancy here is even worse when you do not a log scale, basically. This is something else. And again, the point here is that a lot of people are trying. This is, is a huge effort that requires a lot of attention. But even right now, so this is one of the latest papers, 2019, so I'm not talking about 20 years ago, right now, you see discrepancy. So people still do not know much about the pH's growth. So as a student, as your interest also, if you're looking at an area that you might be, interested in pursuing, I think anything about the chemistry of pHs is very important at this point. Whether it's experiment or modeling, I think there is a niche and there is a need for that. So what we learned about this lesson yesterday is that the pH formation is sensitive also to the flame. So if you remember, I was telling you, if you are in those conditions, you will form acetylene, propargyl, and then you can keep growing. If you are maybe a lower temperature, you do something else. You form more peroxide. So when you talk about an engine, you are more interested sometimes in this low temperature. When you are in a flame, you go more to high temperature. So depending on your system, the precursors, the species that you form in the gas phase will change. And there is a lot of literature about that. So even the lecture that you have in the morning with the Professor Curran from Ireland, he is telling you how to build the mechanism, basically. He's telling you what are the gas phase species, what is the ignition, and all, on those lines, basically. And so the problem is that, and again, what I want to emphasize is that why we don't match. The reason why we don't match with experimental data is, I will say, twofold again. Either you have the pathway, so you have the mechanism, but you don't have the rates that are correct. So you don't know how fast this reaction is happening. And that requires very high-level calculation. There are some groups that do ab initio simulation, molecular dynamics. But the other important things that I think it's more, it's an unknown and it's really a challenge is to think about a different chemistry. So maybe you have the pathways, maybe you have the right rates, but it's not complete. So the mechanism, the networks of reaction is not exhaustive, basically. You need more information that you don't have there. And so the question is, how do you do that? And I'm not going to present here, but one of the avenues that I'm pursuing at this point is the use of possibly machine learning to help with those questions. Because the complexity, I believe, is beyond what a person can do. If you think about that, there is a fuel, and the fuel can have a lot of trajectories as evolves. Those trajectories changes with temperature, with the pressure, with the equivalence ratio. And so the complexity, the dependence of this pathway is complicated for that. So I think, as another point, because my goal here is to tell you a little bit also what is required, and not just to tell that everything is working. So different ways to look at the chemistry is also very important at this stage. In terms of needs, what I highlight here is the resolve the uncertainty, basically, in the chemical composition of the pHs. There is not much literature about the concentration of pHs. So if I want to model a flame and I want to look, for example, at 1 ring, 2 rings, 3 rings, there is not much I can find. And so the rates also, so experimentally that's a requirement, but the rates as well as the kinetic models, I think it's a big challenge at this point. And again, with the morning lecture, you have a feeling of how you build the mechanism. So maybe merging the two needs, the mechanism and pH's formation, could be an interesting step. So let me go back now to this again, one more time. So assuming that we have some gas phase concentration, some gas phase species, that's what you find in the literature. The question is, how do you keep growing? How do you jump from here now to those nanoparticles? And so there are 2 major pathways in the literature that people usually look at. And those are some of the main highlighted that I want you to see today. So there is a physical growth, people call physical growth, and then there is a chemical growth. So let me explain that a little bit. So once you form a pyrene, for example, so one of those big aromatics with the 4 rings, what happens is that some people believe that basically the idea is that one pyrene will stuck together and they will keep growing, basically. So the dimerization, what that means is that the 2 molecules will stuck, and basically will stay together for a long time, so they can be considered the first nuclei on which the gas phase molecules will land. Okay? So one of the physical clustering of pHs is an area of research, greater area of research basically. And the other one is instead the chemical growth. So you still have those pyrene, for example, but instead of stuck on each other, you find a way to make a chemical bond between them. So maybe you have a radical of pyrene that forms with the stable molecules. And so the growth is more kinetically driven in this case. And so the current models for soot formation, basically, that you find in the literature, they define dimerization of pyrene as a nucleation step. So what happens is that you have this gas phase chemistry, your model is producing some concentration of pyrene. At that point, the soot modeling is taking the concentration of pyrene and they say, pyrene is my dimer. I will keep growing with that as my transition to nanoparticles, okay? There are some approximations, but I think what I want to point out is that this is the best we do at this point in this terms of modeling. There is some sensitivity on pyrene, but still he is the favorite pHs in, I will say, most of the models that are available right now in the literature. The chemical pHs also, there is some literature on that, and I'll tell you a little bit with that. So the experiments and the theory are uncertain on the mechanism and the species involved. I want to remind you that the area, the region is very narrow, so even the species that you find are not clear, basically. So an example of this dimerization, so take a look at this. So the idea is that I have pyrene, and now this is my molecules. So what happens when I put them together? So here I'm looking at a result by Professor Miller, Houston Miller, George Washington University. So what he did here, you look at the dimerization, and on the axis you have the number of aromatic rings. And on the y-axis, you have basically the binding energy. What that means is that basically you have aromaticity core in those species. The idea is that what is the size that you need for them to bind? And I know maybe you guys are looking at the slide. I don't know if this was in the slide. So I will upload all the slides at the beginning, at the end of this Wednesday, basically, when this is over. I have to say I changed a little bit based on the question I had also yesterday, so maybe there is more material that you have in the slides, but in the end you will get the final presentation. Okay, so let's take a look at this result first of all. So what this is telling you is the number of carbons. So look at the graph on top. So you have a naphthalene. So naphthalene is 2 aromatic rings and has 10 carbons. What this is telling you that if I have a naphthalene dimer together, the binding energy is, I don't know, around 5 kcal per mole. As you grow in size, basically, when you have pyrene, for example, that is 4, you have a higher binding energy. And if you get bigger, so you have a circumcoronine, that is the last one, then the binding energy increases with that. Okay. So basically, the problem is also now what happened is that, so the top is that. So he highlighted that the translation energy basically of the pairs may be trapped in the momentum of the molecule. So what that means is that he's looking at those 2 dimers putting together and he's computing with ab initio technique basically the energy for them to bind. The graph on the bottom, it basically is telling you something about the relative concentration. So it's true that as you grow in size, the binding is stronger, but the problem is that the concentration goes down, okay? So even if the big guy likes to stay together, their concentration is very low. So there is a balance between, you know, just the attraction and how many of those compounds you have in the flame, basically. So let's see what we could do in a little bit different way, okay? So that was the problem. So remember that basically I have this graph in which I have the time scale and I'm going gas phase, and now I want to transition to nanoparticles. What is the problem that I was trying to solve here? So first of all, the question I had, what are other methods cover and what they cannot for computational physical reasons, okay? So let's say that you don't like molecular dynamics. Let's see what we could do. So CFD. CFD, if you want to look at the formation of those species with the CFD, for example, there is a very limited chemistry that you can include in that. Usually you reduce a mechanism and you have only a few steps to follow what's happening. So the molecule-molecule interaction model is very simplified, and the amount of chemistry or things that you can learn is also limited for that reason. So CFD is used for different goals, not to understand the chemistry, but actually the chemistry goes in as a reduced. Ab initio. So ab initio simulation, like the one that I show you for dimer-dimer, is basically solving the energetics of the compounds, but the problem is that you are very accurate, but you are very limited in size. So pyrene, it's good, but as if you want to grow, remember that we are interested in nanoparticles. This is not possible. It's not feasible that you can solve this high-level calculation with a bigger size and time. The other possibility is what I call deterministic continuous model. So what that means is something looks like also what Chemkin does, the Chemkin type. So those kind of simulations require a knowledge of the chemistry. So you need to know if I have my compound A, what is your final product. You need to know something about the transport also, if you ever solve the Chemkin problem. And also, something that people usually do not consider when they run Chemkin, they are valid only under certain conditions. So you need to have thermodynamic limit and large quantity. What that means is that if you have pHs, or if you have even soot, the concentration in a flame is very limited. So the deterministic continuous model, actually, it's not strictly valid in those conditions. So in principle, you could not apply that, basically. The other option is experimental technique, right? So, and none of those, basically, they can give you some ideas, they can give you a glimpse, as I was mentioning, but really they don't allow you to follow the entire growth. So they cannot give you information about the species formed very easily, and they have usually like a lower information, so before the transition and soon after the transition, okay? So it's up to you to fill this gap between the species. So what are the phenomena? So I'm still trying to find a way to bridge those scales and trying to be more specific about the simulations. So the phenomena that occur on the nanosecond and nanometer time and length scale, because that's what you're interested in. You're forming nanoparticles. So you have molecules, nanoparticles that are interacting. You have energy transfer between them. So there's a lot going on here. You have reactivity between them, so they can react when they're growing. And all this is basically forming with the soot precursors. So you have pHs that are forming. You have maybe nanoparticles that start forming the first nuclei, and then you have nanoparticle molecule reacting. So it's complicated, again. And so what can we do with the accurate description of this phenomena? So your goal, basically, what we are trying to do is to find a very accurate way to describe this. Once you have them, you can simplify and feed them to a CFD, so again, just what. But also, the idea is that if I have this model that is pretty reasonable, then I can understand what are the main mechanisms that are driving the growth, right, of the species. So that somehow, eventually, you can control them. I think that's the whole thing. If I have to choose a model, usually, this is what I look for. So if you are choosing an approach that you're interested in, those are what I will say as a requirement. So all these slides, guys, is just to make you sure that I kind of build my story to get you to molecular dynamics. So up to this point, I told you there are species, they don't match, something is missing. You can do CFD, you don't learn about chemistry. You can do ab initio, great, very accurate, but only small size. We need something different here. So when I look for a method, what are the requirements? So here I listed what usually I think about. So make minimal assumption on physical and the systems, on the physics of the system. assumption is to be based on physical equations, so no phenomenological or empirical numbers, okay? Because otherwise it's not what I'm interested at this point. They need to be able to cover a nanoscale, millisecond time scale. You remember the graph I showed you? There was this huge time scale difference. They need to provide an atomic resolution, but still being able to describe nanoparticles. And so also be able to describe reactivity. Okay, so it's a lot of requirement. But this is my ideal list of things that I would like the methodology to be able to do. And so, what are the computational techniques that fit the bill also? Molecular dynamics and kinetic Monte Carlo. So today, I'm going to tell you a little bit about molecular dynamics. And tomorrow, we'll do the kinetic Monte Carlo briefly with the code I've been developing over the last years, just to give you an idea. So again, the story is I need something different. I need something with those requirements. What am I looking for? What am I going to choose? Molecular dynamics. So molecular dynamics is basically the ability, they can follow the evolution of a molecule, atom by atoms, basically, over time. So it's the dynamic, basically, of the system. It's very detailed, but covers up to, let's say, microseconds, okay? Molecular dynamics also has a limitation in size and time scale. I'll show you what that means today. So computational intensive, usually, if you have a bigger system, they could become, depending on the accuracy that you want to use, they could be computationally, very consuming. But some of the things sometimes are not interesting. For example, think about this. You put in like you want to simulate, you have a box of pHs, okay? Sometimes, let's say that you run for, I don't know, 1 microsecond. They just dance, they don't do anything together. So part of the simulation sometimes is just for them to just moving in the box, like in the gas phase. And in the end, what you want to see maybe happen on a very short time frame, basically. So the other thing is that you choose molecular dynamics, but you have to be careful because you want to choose in a way that is interesting, not just putting things in a box and waiting for days, hopefully that something will happen, okay? That's a waste. The other thing that is kinetic Monte Carlo. So Monte Carlo is a stochastic method, so you might be familiar with stochastic method, and kinetics means it is driven by the rates of the reaction, okay, so the temperature if you want. The computation requirement is minimal compared with the molecular dynamic simulation. It can cover up to seconds, so the time scale is a little bit different if you want to. But it requires some knowledge of the events. So those are the two main differences. And I'll show you exactly what that means in a while. So molecular dynamics, there is no bias. The system will evolve, but the time scale is limited. Kinetic Monte Carlo can go farther in time, but you need to have some knowledge of the event. Okay, so let's talk a little bit about atomistic simulations at this point. Again, the goal is to look at combustion here. So I don't want to take you too much away from combustion, but I want to give you a little bit of things. So this is an example. If you learn a little bit about molecular simulation, atomistic simulations, you can basically use them for many applications. And this is a point I want to really highlight here. One of the reasons why I love those simulations is because they give you power to look at different systems, okay? It's not a technique that you learn and you can only apply, I don't know, to a pH or to a combustion question. But you can kind of broaden your view of problems and shape molecular dynamics for other problems, for other systems. So tomorrow I'll show you an example of what we have been doing with biology also with the same technique. So atomistic simulation can be you calculate energy of the system, for example. But they also, for example, if you're looking into material science, you can predict the failure, the fracture, for example, of a material. Adhesion is another one, diffusion constant. Think about, even when you run Chemkin, if you run a simulation with a flame, you need the transport, right? So diffusion coefficient is something that usually you take from a library, but if you want to be accurate, then molecular dynamics can help you with that. Some of the hypotheses that you use in the equations are based on molecules that are spheres, basically. If you do the diffusion constant with the molecular dynamics, then you can take into account the shape of the molecules. Wave speed, phase diagram. So if you have one of the applications right now moving a little bit away from just the single combustion problem is nanomaterials in combustion. So people use flames to produce a specific nanomaterials. And so alumina is one of those. And the idea is that what happened to alumina nanoparticles in a flame. And so, for example, the melting, it's very important. The inorganic material can have a different phase. Once you are at a high temperature, it can change phase. And so MD can give you information about that. One of the projects I want to show you tomorrow is about alumina in a flame. So we had a collaboration with a material science person in which he was producing nanoparticles in a turbulent flame of ethanol, and ethylene was the flame. And the question was that they had some precursors. So the question for us was, I like to produce alpha aluminum that is more expensive, for example, but I ended up always with the delta phase, so a different phase of that. So the question was, how can I channel, if you want, my pathway to leading to alpha instead of delta? Okay? And so what you could do with the molecular dynamics is basically taking a nanoparticles of alumina, in the same way you will take a nanoparticle here of combustion, and see what happens when you put in high temperature in specific conditions. Okay? Protein folding, if you're interested in biology, is something else that you can play. And so for materials, yes, you talk about failure of the materials at the macro scale, but what that means is that at the atomistic scale, you're tearing a bond, for example. Okay, and so the question is, can you link the breaking of this bond with a macroscopic process? Disease, it's a big word, as a macroscopic word that you see, but in reality, what's happening is maybe unfolding of the protein that is happening. So this is another, just again to tell you that you can do a lot of things with molecular dynamics. So even something that looks, okay, you can think about, but is very far from what you usually will, like a mad cow disease, that is caused by a protein misfolding. So molecular dynamics, same way, you can look at how does a protein can unfold or misfold in different biological systems, for example. Another things on the right is the drug delivery or drug evolution, basically. And so what that is that you can design some drugs knowing how they bind, for example, with a protein. Okay? And again, it's a question that molecular dynamics, with some assumption, can help you answer. Very detailed answer. Now, whether you're using MD or kinetic Monte Carlo in more details, we need to be careful about a few things. So the goal here is to show you a little bit the potential, but also the problems, okay? Because people sometimes do work and they don't pay attention to those characteristics of the simulations, if you want. So when you run a simulation, you have, let's say that you have your molecules. So think about things like that, okay? And over time, you want to see what happened to this molecule, okay? Is it folding, is unfolding, whatever you're interested in. How fast it diffuse. The question is, the problem is that each simulation runs a single pathway, okay? And so, but that's not what happened in reality. So one of the problems we have seen in the literature also, that people sometimes run one simulation and they think it's the answer to their question, okay? So the problem is that you cannot do that. You need to think about an ensemble. So this is one of the first words that we're going to hear today. An ensemble is a collection, basically, that you're in. So in principle, you run many, many trajectories and you have to average what's happening, okay? So one of the main problems is that how do you translate? How do you translate between those two words? So you, in an experiment, you measure temperature. You measure temperature of molecules in a tank, for example, from my molecular dynamics, I just see a box with the molecules inside. So how do I translate what's happening to the molecules to the temperature that you read with the thermometer? And the transition between those two words is very, very important. So something that you want to pay attention to when you run. So macroscopic versus atomistic property are not always easily connected, okay? And again, there's a literature in which they just run one simulation and you get to the macroscopic world. That is not right to do. Macroscopic world has a large number of quantities like pressure, temperature, density, viscosity. I think that those are the macroscopic properties that you understand somehow. But molecules are defined by position, so velocity and properties. So you have to find a way to connect both of them. And so the macroscopic is basically a result of the distribution of the atomistic observables that you have. And the translation between those two words can create problems, for example, okay? So before I give you more details about MD, I want to, again, use some basic definition here, like we did yesterday a little bit. So what is a model? A model, when I talk about molecular, so we want to differentiate between model and simulations. People usually use this interchangeably. So a model is an idealization that you have. And so the ability of how good is this model is how well it will reproduce some condition. It can be a description of a data, that could be something easy, or it can capture the physics. Okay, my model is so good that I can talk about the physical aggregation or the chemical growth. Okay, that's a model. A simulation is the procedure of solving the equations, okay, that resulted from the model development, basically. And so numerically solve a set of differential equations with some initially boundary condition. That's the simulation that you're running. So as a first step, before we get to MD, let's talk about microscopic to macro scale. So how can we compute macro scale properties? Macroscopic states, you have many, many different atomistic configurations. So let's say that you want to talk about the diffusion of nitrogen gas in a certain temperature. So you have a tank, you have a box with nitrogen molecules inside, and then you have a temperature that somehow you are setting for the simulations. If I run my molecular simulations, what I see on my computer is something that looks like this. So at different time, my system is evolving, but I have configuration 1, 2, 3, 4, going over time, right? What you see in the tank is a temperature from the thermometer. You see a pressure, a volume, or the number of particles, and so on. So an ensemble is a collection of microscopic states that are consistent with the thermodynamic boundary that you set in your system. Okay? So you talk about ensemble, you don't talk about single configurations if you want to translate to the macroscopic region. And so how we calculate the property from atomistic simulation, the answer is statistical mechanics. And it's not, I don't want to tell you a lot about this, but this is what usually, if you come, for example, to my group to start learning molecular dynamics, the first thing that you want to read about is statistical mechanics, okay? So with that, basically you learn the fundamentals that can help you also with the MD simulations, basically. And so it bridges the macroscopic world with atoms, basically. So there are some assumptions, something that you need to take into account to make this jump. So again, macroscopic systems is defined by extensive variables that are constant. So N is a number of molecules, volume, energy. What we see is just molecules moving in a box. So the large, when you run the simulations also in your system, you have to decide what you are interested in computing and what are the properties that you want to keep constant, for example. And so one thing that we'll see throughout molecular dynamics is that you can choose different systems. So you can define your box with the molecules inside. You can run microcanonical, that means NV. So what that means is that N is the number of molecules, V is the volume, E is the energy. So canonical is MVT, temperature is constant, isobaric, isothermal, NPT, and grand canonical. Now, this seems to you just like a definition of, not so interesting, but already if I ask you, in combustion, which one would you use? Are you using something that is a constant energy? Are you using, like if you want some molecules in a flame, for example, which one would you use? That's not a clear answer yet. And sometimes people make a mistake when they define the simulation. For example, if you're doing like a reaction in a flame, MVT, for example, the volume is changing. You have new products that are formed, okay? Is the temperature constant? Well, if you move along the flame, the temperature is changing dramatically. So are you keeping the energy constant? What are you keeping constant? It's a big question when you run the simulations. So the first thing you need to understand is I have my system. I need to define some boundary condition for my system that I can apply to my molecules. And the other point I want to make is that we need to be careful at this point if I run my simulations, and what does that mean from a macroscopic point of view. So we're going to talk a little bit about the temperature, pressure, the molecules, and the volume at this point. So here we go, molecular dynamics. So again, the job here is to give you a glimpse of this technique, and I'll be happy to answer any question during the break or whenever you want. And I'm sure that you have a lot of questions at the end, because there's a lot that you can learn about molecular dynamics. But I want to give you some ideas so that by the time we are done today, you will be able to think about, I think you could be able, if you were like in front of a computer slowly, by this time you will be able to set up simulations. So you can tell me exactly how you start, okay? You will tell me something about, once you have trajectories, how can I analyze them? I mean, what do I do with this bunch of trajectories and numbers? What kind of property can I get? That's what and then, last, that I just briefly mentioned at this point, I want to show you how you link to microscopic property. So if you have a trajectory, say the temperature over time, what's doing in your system, what does that mean in terms of the temperature that you measure, okay? And so one of the things I brought here is, remember that we want to talk about combustion. So again, I don't want you to verge too much into chemistry, but I want to make sure that what I say, it's relevant to combustion. And so my MD, just to give you an example, I was interested in something like that. So remember that I have my pHs, right? They need to grow, and I don't know how to make them grow at this point. So one of the things that I was asking to molecular dynamics is that, let's say that you have a box with a bunch of those pHs coming from the gas phase at this point. Do they stick together? Do they like to play, if you have a different temperature, will they collide with each other? If they find the big molecules, in this case it was just represented by a fullerene, there was a big nucleus. Do they stick to this nucleus? What kind of attraction do you have? So from an experimental point of view, what they see when they sample nanoparticles and soot is that you have a core that is amorphous, if you want. By amorphous means that what they call also liquid-like. So it's not a sphere, like a solid sphere, but there is some variability in the core. And then eventually you have those gas phase species from the gas phase, basically, that cover this core, and they keep growing in size. And so the goal was to use molecular dynamics to answer some of those questions for combustions. Okay, so I guess before we start with molecular dynamics, maybe we can take a break. It's 3, and then we'll look at the simulations from MD, okay?